equation. From these two equations, this one and this one, you can see that the tangential component of B are continuous at the boundary, while the condition that the boundary is with the condition at the boundary is current free. So if K or I equals 0, B tangential 1 equal B tangential 2. So if you do the parallel with the electrostatic field, all right? You would have E tangential 1 equal E tangential 2, and B normal 1, no, E tangential 1 equal E tangential 2, and D normal 1 equal D normal 2. Now, if you draw the similarity with the magnetic field and say you're going to call H for E and B for D, it would flip. So H normal 1 would be equal to H normal 2 and B tangential 1 equal B tangential 2. Okay. So look at some angles. Let the fields make angles alpha 1 and alpha 2 at the boundary. So we can write tan of alpha 1. Look at it now. This is your B field. Okay. So tangent equal what? Tangent equal
opposite over adjacent. So B tan over BN
over B. This over this. And similarly, this will be this over this. Tan of this. So equation 17 divided by 18. would have this. Note this statement. Based on this example, note this statement. Okay. All right. So we're gonna do some, in Unit 4, we're gonna do some interesting stuff now. Magnetic potential and vector magnetic potential and its properties. So vector magnetic potential due to simple configuration, vector Poisson's equation, self and mutual inductance, Newman's formulae, determination of self-inductance of a solenoid, toroid, and mutual inductance between a straight long wire, a square loop wire in the same plane, energy stored, intensity in magnetic field. We're going to look at those. So in studying electric field problems, we introduced the concept of electric potential that simplified the computation of electric field for certain type of problems. In the same manner, let us relate the magnetic field intensity to a scalar magnetic potential. So H, remember, in electrostatic field, we have E equal minus del V. So in magnetic potential, we have H equal minus del V. The subscript M is saying that it's a magnetic vector potential. And we have, from Ampere's law, del cross H equal J. So let us just do the maths. So we're gonna substitute the H here in this. So we have this. Use the vector identity. Vector identity. Okay, help me with this, Mr. Duncan. Del cos del V equals 0. Find H equal minus del V is valid only when J equals 0. Okay. You get that?
So, so what I get from this is fairly that this equation that they derive from substituting Ampere law can exist because apparently it is also identity where it must equal 0. So essentially they're saying that scalar magnetic potential using this equation where we substitute H for minus del V of M.
Can only be when J equals 0.
Yeah, that's all I get from it.
Which is right. Thus, the scalar magnetic potential is defined only in the region where J equals 0. Moreover, Vm in general is not a single valued function of the position. So let us consider this figure. So we have region A is less than rho, which is less than V. Here to here is B. Here to here is A. So A less than rho, A less than rho, less than B. So rho is any length here. So A is less than rho, which is less than B. So we are talking here, this region. J equals 0 and we know from before that H equal I over 2 pi rho A rho. So H equal minus del Vm. H is this. Is equal minus del Vm. See if you get that math.
That's the cross product the cross product curl of VM, right, sir?
Yeah.
Okay.
Get it?
Yes, sir.
Okay. So now we introduce the magnetic vector potential, which can be used in regions where the current is zero or non-zero. Thus, the use of vector magnetic potential provides elegant ways of solving electromagnetic field problems. Since del dot B equals 0, and we have the vector identity that for any vector A, del dot del cross A equals 0. So this is the identity. So we can write B equal del cross A. Del dot B equals 0. Using this identity for the vector, we can write this equals 0. So if you digest that, it's straight maths using the vector identities. I'm giving you a chance to follow that. Any question you start, raise it.
So you're going to go back over the maths operator to fully understand what's going on.
The maths operator, what do you mean?
No, the maths. I'm going to go back over the operator, the del operator.
Oh, okay.
Yeah.
You mean you have to go back over that?
Me, yeah.
Yes, sir. The same situation. It is a bit too much to, completely grasp. I just looking at it one time. So once you go over it a couple of times, you understand.
All right. Yeah, because that is the early maths. But anyway, you will arrive at this, where the magnetic flux is the integral of B dot ds. Which is where we want to arrive at. Because remember, in networks now, how them present it again? What
Represent what, sir?
what them call it now? Inductance and mutual inductance and all of them. So,
Yeah.
how them equation they go again?
LDI over DT.
Right.
We do that more in
Networks.
drives and machines one than networks. Although LDI DT networks as well.
Mm-hmm. Anyway, here's a big statement. Resistance, capacitance, and the inductance are three familiar parameters for circuit theory. We have already discussed about the parameter resistor and capacitor in earlier chapters. In this section, we discuss about the parameter inductance. Before we can start our discussion, let us first introduce the concept of flux linkage. If in a coil with N closely wound turns around where a current I produces a flux phi, and this flux links or circulate or encircles each of the N turns. The flux linkage, what does Greek symbol mean again? Flux linkage, let's call it flux linkage. The flux linkage is defined as N phi. In a linear medium, where flux is proportional to the current, we define the self-inductance L as the ratio of the total flux linkage to the current which they link. So L inductance, self-inductance equal flux linkage over I. But flux linkage equal N phi, that's N phi over I. Let's look at the figure. So this is the figure. So we have two loops, C1 and C2. S1 is the surface of loop 1. S2, the surface of loop 2. So I1 flows through C1. The magnetic flux B1 will be created, part of which will be linked to C2 as shown. All right. So this will produce a magnetic flux which will link. These lines are flux lines due to C1, right? But you see, some of the lines will link C2. So phi1, which is the integral over S1b dot ds, in a linear medium, phi1, 2, that is the flux due to 2 and 1 is proportional to I1. So phi1, 2 equal the inductance 1, 2 times I1. See if that makes sense to you.
Makes sense, sir.
Make sense?
Yes, sir.